Welcome back to the workshop for another example in directed graphs. What we want to do for this example is we want to utilize the breadth-first search algorithm adapted for directed graphs to help us find distance between vertices and shortest paths. So we're going to apply the breadth-first search algorithm, but we're going to focus on making sure that we're traveling in each case in the correct direction along each edge. So for part A, we want to find the distance from C to E and give the shortest path. Of course, this example on its own might be sufficient, but I'm really excited to include a second part where we travel back from E to C. So first, let's travel from C to E. Now, for starting at C, the distance from C to itself is 0 with no predecessor, okay? No vertex before it in the shortest path. Now, the breadth-first search algorithm says to label each adjacent edge as a distance of 1 away. But we want to be very careful there because we can only travel one direction along each edge. So traveling in the correct direction away from C, having out degree 1, that gives us the ability to label one vertex. That vertex is B, and it is a distance of 1 away from C, and its predecessor is exactly C. Awesome. So now I have B labeled, and I want to increase my labeling again and find the vertices that are a distance of 2 away from C. Okay, so I can travel in only one direction, so B has an out degree of 2, and that will allow us to label 2 vertices, those that B travels to, so B to E along this edge. So that gives me the ability to observe that E has a distance of 2 from C with predecessor B. D is also a distance of 2 from C with predecessor B as well. Of course, if these edges were not directed, this would be a distance of 1 away. But the edges are directed, so I could not travel along this edge to get to D. All right. I've labeled everything that's adjacent to B, and now I can spread out a little bit further and look at everything that's adjacent to D and adjacent to E. There's nothing unlabeled adjacent to D, so I move on to E, and I say, all right, well, that gives us the ability to label A as having a distance of 3 from C with predecessor E. Excellent. We've actually already found what we need. Well, of course we have because we've labeled everything. But we found it in the previous step where we labeled E. E has a distance of 2 from C. E is 2 away from C. Excellent. We could say that a little bit better maybe as the distance from E to C is 2. Excellent. And then the shortest path, or a shortest path, there may be multiple, in this case I think there's one. The shortest path is, and of course we're looking at a directed path here, but the shortest path is we'd start at the end, and we wanted to end at E. Its predecessor was B, and the predecessor to B was C, exactly where we wanted to start. Okay, so CBE is the shortest path, a path of length 2. Excellent. Now, I really wanted to include the second half of the example because it really highlights what happens when we can't travel both directions along any given edge. So again, we want to find the distance, but it's order matters here, right? We found the distance from C to E, and now we want to find the distance from E to C, so going the other direction. And again, we want to give the shortest path. So now we have to start at C and beginning at, we have to begin at E, and beginning at E, well, that's 0 away from itself with no predecessor. Now I can travel out only along this edge, giving me that A is a distance of 1 with predecessor E itself. Well, now from A, there's only one direction I can go, right? I still can't go out anywhere else from E. I've already labeled A, so now I have to travel along this edge. That's the only way that I can go to get to B. So this is a distance of 2 with predecessor All right, now, again, there's only one place that I can go, right? I still can't go anywhere else from E, still can't go anywhere else from A. The only place I have to go, the only next thing, the only adjacent thing, it would be D. I can only move along this edge to D. So D is a distance of 3 away from vertex E, having predecessor B. And then finally we can get to C and say that C is a distance of 4 because we had to get to D and then go to C, a distance of 4 away from E, having predecessor D. So the distance is very different in this case. It's twice as far to go from E to C as it is to go from C to E. Okay. The distance from E to C is 4. Excellent. That language looks a little bit better than what we said over here. All right, and then finally, the shortest path. From E to C is, again, we'll work backwards, ending at C. The predecessor to C was D. The predecessor to D was B. The predecessor to B was A. The predecessor to A was E. Excellent. This gives us our shortest path, having a length 1, 2, 3, 4, counting the movement from one vertex to another. Okay? Distance of 4, this path has length 4. Excellent. One more example to talk about for directed graphs. So I will see you guys here in the workshop again very shortly.